Prairie dogs are small social rodents that live across the North American Great Plains. Beneath the surface, they've engineered a remarkably clever ventilation system. Their underground colonies stretch for miles and house thousands of individuals. These burrows protect them from predators, regulate temperature, and create safe spaces to raise their young. Prairie dog tunnels are surprisingly long, about 10 to 30 meters, with narrow passages just 12 centimeters wide and chambers 1 to 5 meters deep. Diffusion alone can't deliver enough oxygen. Prairie dogs rely on wind-induced pressure differences to ventilate their burrows. To create these pressure differences, prairie dogs build two types of entrances, a lower rounded dome mound and a taller, sharper crater mound. When wind flows over uneven terrain, these shapes generate a pressure drop that drives airflow. Air flows in through the lower dome and out through the higher crater, forming a passive wind-powered ventilation loop.
For our project, we wanted to understand how prairie dogs use their mounds to ventilate their burrows using just the wind. To study this, we 3D printed simplified mound shapes based on the geometry from a research paper. From each mound, we attached plastic tubing to mimic the underground tunnel system. To generate the required wind speed, we used a small fan directed at the mound. We also printed small holes in the mound so we could insert an anemometer and measure the airflow inside the tunnel. In this picture, the red arrows show the direction of the external wind across the mounds, and the blue arrow points to where the anemometer sits inside the tunnel. This setup lets us measure how pressure differences created by the mound shapes drives the flow through the system. For the demonstration, we took our setup to the roof so we could use the natural wind instead of the fan. With the tunnel connected between the two mounds, we released smoke into the lower mound. The natural wind created a pressure difference, and we were able to clearly see the smoke travel through the tube and exit from the higher mound, showing how prairie dogs naturally ventilate their burrows.
We examined how different mound curvatures influence airflow using three mound shapes while keeping the fan speed and tube height fixed. The trend was consistent. Greater curvature produced higher velocities inside the tube. While we haven't isolated the exact mechanism, a reasonable postulation is that increased curvature guides more of the external flow toward the tunnel entrance, reducing losses and helping accelerate the air. So curvature appears to play a significant role in enhancing the flow. We also varied the vertical tube height from 80 to 140 millimeters while holding curvature and fan speed constant. The results showed that taller tubes led to higher exit velocities. A plausible explanation is that a longer tube provides more length for the flow to develop and accelerate under the pressure difference created by the fan. Finally, we built a simulation to visualize how the air moves inside the tunnel. The flow pattern becomes clear, and we even see signs of steady behavior. This gives us a qualitative picture that matches the trends we observed experimentally. We did not have enough time to fully recreate the exact experimental setup or compare numerical values directly, but the simulation still provides a strong visual validation of the overall flow behavior.